Dave Luthria. I am with US Department of Agriculture. So in the morning part, you had interesting lectures on gut microflora and microbiomes. What I will do is I will switch our gears to Dr. Rana's presentation from MWay, where he talked about extractions. And though I will be talking about influence of sample preparation on phenolic phytochemicals, this can be applied to any of the nutraceutical products that you develop. And the challenges with that is what I'm going to discuss about it. This is a outline of my today's presentation. Oops. Okay. So this slide shows basically I would be talking about brief introduction on phenolics. I will be talking about influence of extraction techniques and conditions, because whenever you are developing a nutraceutical products, we are not selling the products as a plant or something, we are selling it as an extract. And what are the challenges and how these extraction techniques can influence the product. And this is probably the most important variation. When you see in the news, all the nutraceutical products, this is active, this is active, this is active. So if you open up any CNN health news, you will see like all the different products in the world are active and good for health. And I would give some examples about whole and refined grain products, because there has been a lot of interest in whole grain products and their bioactivity. And finally, I will talk about significance of processing. And lastly, acknowledgements, basically the people who do the work, because I have postdoc fellows and other people who do the work, so I'm over here presenting it. This is phenolics. Generally, the consumption is phenolic is a compound basically which has an aromatic ring with a hydroxyl group. Anything which contains this can be termed as phenolics. Misconception is phenolic is certain group of compounds, but when you look into literature, they can be polyphenols, they can be simple phenols, they can be miscellaneous products. If you look at polyphenols, they can be tannins, which can be gallic acid polymers, which can be catechin and apicatechin polymers. When you look at flavonoids, flavones, chalcones, flavonols, flavonones, etc. So there are so many groups of flavonoids. When we come to simple phenols, we can say phenolic acid. These can be hydroxybenzoic acid derivatives or hydroxycinnamic acid derivatives. When we talk about miscellaneous lignans, lignins, coumarins, several other products, whichever has this basic moiety can be termed as phenolics. In fact, while I was digging into the literature, I could find that there are about 5,000 to 8,000 phenolic compounds reported in the literature. The chemical nature varies from a simple monomeric form to the highly polymerized forms in tannins. They occur in free forms. They occur in conjugation with sugars and other molecules. Their stability varies. Some are very stable, some are highly unstable. And their distribution is uneven, and their association with the sample matrix. So this will all impact what you ingest, what is bioavailable, what is the activity associated with these compounds. Next we come to plants are like biological factories. They are not like chemical factories where you produce A plus B, you will get C. But if you go through plant, there is plant to plant variation, there is cultivar variation, there is environmental conditions, how we post-harvest, what is the maturity, what is the extraction method. These are all the factors that keep on becoming variable, and therefore you see in the news, this is very active, this is not active, this is a highly extract. So how you prepare it, how you understand these factors will impact your bioactivities. These are the key steps for analysis, basically sampling, sample preservation, sample preparation, and separation and detection. If you look at any chromatographic journal, any food science journal, most of the publications deals with separation and detection. Yesterday, Dr. Rana said one thing, garbage in, garbage out. So whatever you put into an instrument, it will detect only what you are giving it. It will not produce something else to detect. And basically what you do is how you prepare the sample, how you preserve the sample, how you prep the sample. These are foundations, these are the key building blocks, will determine what you get in your analysis. When I talk about sample preparation, I will be talking about all these factors, which are just ignored a lot of times because we are working with the fancy tools, tandem mass spectrometry, hyphenated technique, LC, NMR, MS. We are combining all these things, but we are not really understanding what we put in. This is an example from a USDA database, basically. These are all peer-reviewed publications. You can see that any of these products that you take, you can see variations in the reported values of phytochemicals by 3-folds to 10-folds to over 20-folds. So there's so much variation in these values. How can the bioactivities and how it will transfer to bioavailability and bioactivities? This is an example of a product, like how we prep our sample. Artemisia annua. Artemisia is like an artemisinin is the best known anti-malarial nutraceutical type products. And basically, if you see that these compounds have high in phenolics, but how you dry your sample? This is an oven dried in front of nitrogen. This is freeze dried. This is shade dried. This is sun dried. You see the amount of phenolics being decreased. So how you prep your sample will have a significant impact on the quality of product that you are producing. This is another example, just shade dried. If you look it over the time, if you leave it for 3 weeks, hey, half of the thing or 70% of the thing is already gone. This is an example of an onion peels. Basically, there are many products, but these are the 6 major. Most are quercetin metabolites. And what you do is, actually, I had a student who was doing the work. High school student, she came, I want to do research. I said, very good. So I said, okay, what you will do is you will take the peels, each peel separately, the outer layer, the dry skin, the second peel, the third peel. Basically, if you look at it, the concentration of phenolics in the first three peels, if you go down, it goes logarithmically. If you take a real onion and if you chop it out and you take the 2 first layers out, you are almost losing 80% of the phenolics if you are interested in phenolics. And then if you do a study with animal study or you do any human clinical trials, all the results will vary because how you prep your sample will signify how much amount of nutrients you are taking in. This is another dietary supplement, black cohosh, which is widely used. It is also rich in phenolics, but if you see how you prep your solvents, which solvents you take, you will see wide variations in the phenolics that you have. This is from soybean. When I looked at soybean, rich in isoflavones, well-studied study, all the papers that were dealing with isoflavones had used either this solvent or this solvent. Basically, when I looked at isoflavone and I went to a simple Merck index, which is the Bible of all the chemistry, they give you solubility, they give the, they said isoflavones are not even soluble in acetonitrile. So what I did is, if you use 5%, you increase your yield by double. So how you are doing your bioactivity, how you are doing your animal studies if you don't even quantify what is there in your starting material. This is another example. Ginkgo supplements are widely used. Actually, we did a lot of studies with ginkgo. The easiest way to collect ginkgo leaves is during the fall because everything is fallen down. You just pick it up, prepare a supplement. But the phytochemical composition of ginkgo leaves is totally different in the fall compared to when they are on the leaves plant. And here, if you see, these are all flavonols. These are bioflavonoids. And the interesting part is, these are other compounds that are found in ginkgo, but the interesting part in this was, if you look at extraction methodologies that you use, you will miss, if you work with a lot of papers in the literature, they show that these are the solvents used for extraction, preparation of extract. If you take these solvents for extraction, you are actually missing the whole lot of compound that is bioflavonoids. This is another example. Basically, we were doing an experiment with parsley. We had made several progress on this. This is apin, which is an epigenin glucoside. And all the time, my student used to give me this trace, and I was very happy to see every time, and we are trying to quantify and develop methods. But what happened is one fine day, he showed me this trace. I said, man, suddenly what are you doing it that is making your phytochemical profile totally different? Here it's mostly one product, here there are two products. And actually what he did was actually reverse the solvent 70-30 to 30-70. Just doing that thing changes the profile and changes the amount. And basically what we saw is, this is actually a myelin conjugate of apin when we elucidated the structure. And if you look at the database, you will see that variation in apigenin content in parsley varies from 0 to 70 milligrams per gram, which is huge. And this is because some people only use apigenin as a basic moiety and identify. Some people take glycosides also and identify. So how you are doing these studies, if you have to understand what is the basic structures that they can handle. These are all the other parameters that we studied. These are like solvent composition. I've shown you several examples. These are temperatures, what you extracted. This is particle size. Basically, you can extract double the quantity if you reduce the particle size, which is general basic chemistry. But if you don't follow those things, we just ground the particle. Look at any of the literatures, like I'm in the associate editor for the journal. In the materials and methods, if you look at it, ground material was used for analysis. What does ground material mean? Doesn't mean anything to me unless you say what is the particle size. Now we'll switch gears to grain. Basically, what we do is refined grain basically lacks these three things: bran, endosperm, and the germ. It's mostly the endosperm portion. Bran and germ are missing. And when we look at the phytochemical compositions of different grains, you see that the amount of phytochemicals that are distributed in the germ, in the bran, in the whole grain, in the refined fractions are much, much different. This is what you get in the refined sections. And these are the phenolic compounds that we have isolated. If you look at it, if you take the refined flour, there is practically nothing. They are all in the same scale. Whereas if you take the wheat bran or the whole wheat flour, there is significantly higher in the wheat bran fractions. What we did is we took a grain and we started shaving the grain. Every time we shaved 5%, we took it separately and we tried to analyze it. If you look through it, almost like when you reach 50%, you have almost taken all the nutrients out of the thing. Endosperm is mostly the starchy portion of the grain. The next thing is, how are these phytochemicals there in the grain? Are they present in the free form? Are they easily bioavailable? Are they associated with other components? And if you look at these studies, basically, if you look at these are soluble free form, which is right over here. There's nothing in the soluble free form. Over 90% of the phytochemicals are in the bound conjugated form. They are not easily available to you. So we have to understand how these phytochemicals, these are like biological factories. So you have to understand what bioactive phytochemical is there, what are the different forms it can be present, how they are presented, what is their association with the cellular matrix. This is basically what we were doing is we were trying to extract it. Nowadays, a lot of modern extractors are there like microwave, ultrasonic and all. What we were doing is when we were doing microwave extraction with wheat flour, what it was happening, it was gelatinizing, it was cooking up, it was swelling, it was forming a gel. And as soon as you form a gel, the phytochemicals are being trapped, so your extraction efficiency reduces significantly. This is one of the examples that we discussed about how the secondary metabolites. If you look at it, we have done extractions with hexane, ethyl acetate, methanol, which are increasing polarity. We did direct extractions with water. What I'm saying is how you extract it, you can see how the metabolites can vary in all the different grains. And these are the metabolites that we were identifying it and we were trying to identify. So how you prepare your sample, how you formulate your things will impact your metabolic profile, will impact the extract profile, and it will definitely impact your bioactivity. And this is basically showing that when we looked at different food materials, we cannot treat all the food materials in one way. If you look at black bean, if you look at soybeans, they were all extracted with different solvents, but very close similarity. But when we looked at black cohosh, each of the extracts with different solvents have different things. So we cannot use a standardized methodology. We have to understand what these methods are. We have to understand how they existed. And these are other processing. So I will switch gear. How do we eat wheat? We don't eat wheat raw, basically. We make it into a bread or something. These are the bioactives that are present in wheat. And what we did is we prepared the bread out of it, and we took it like how this is the most heated surface, the upper crust and the bottom crust, because they are touching the hottest part, and then these are the crumbs. And what we did is we did analysis of these things. If you look at phenolic acids, they are not degraded much, but if you look at upper crust of tocopherols, upper crust of carotenoids, they are degraded when you heat it. So we have to see how the processing does it, and what does processing do to these phytochemicals. They don't treat all the phytochemicals in the same way. And finally, if I have to conclude, is like what I wanted to say is phytochemicals are not uniformly distributed. I showed you with an example of a quercetin. I showed you with phenolic acid. So we have to understand how these phytochemicals are distributed. We have to understand how are they in free form or conjugated form. We have to understand what methods to use extracted. And it is really, this would help us in understanding the total amount of phytochemicals that is getting inside the body, and what is bioavailable and what is getting excreted out. And I showed you with the whole, and the processing does influence the amount of bioactives, and we have to understand that thing before we develop nutraceutical type products. And finally, I would say that we did find while we were making the bread, phenolic acids were not reduced. They were reduced to a certain extent, but they were replenished by the conjugated bound phenolics. They were continuously being released. There was significant degradation of carotenoids and tocopherols, and concentration of and the metabolic profiles will be very, very important to understand how a nutraceutical product affects the bioactivity. And finally, I would like to thank all my colleagues at USDA, because a lot of this work has been done by students and postdoctoral fellows, and also collaborators, because a lot of these samples that we get are authentic. They are provided from a known source with known germplasm and everything. So that is very important for us to do this study. And thank you for your attention.
Any questions? All right, if it looks like there's no questions, we can do some certificates, and we can break for lunch.